For centuries, we have mapped the solar system using a single foundational assumption. We picture space as an empty, geometric void, where planets are suspended in a vacuum, kept on their tracks by the invisible tethers of gravitational attraction. This technical diagram shows how that standard astronomical model forces planetary paths onto perfectly smooth, continuous elliptical curves. This geometry relies on the assumption that space itself is a perfectly smooth, uniform stage. However, a disconnect appears when we analyze raw, unadulterated hardware telemetry. The actual coordinates of these planets, recorded by our instruments, frequently diverge from those idealized textbook ellipses. Instead of tracing gentle, predictable curves, the raw coordinate data clusters into sharp, high-shear phase boundaries. These are abrupt mechanical transitions in space, like the asteroid belt, where objects gather in ways that the smooth pull of gravity struggles to explain. To bridge this gap between theory and observation, standard models must introduce unseen variables like dark matter halos or complex orbital resonances. When a map requires constant patching to match the terrain, it suggests the foundational map no longer reflects reality. Mapping these sharp, clustered boundaries requires a different perspective. We have to treat space as a hypertense pressure field, a physical medium that reacts to movement and density. By setting aside the gravitational constant and mass tethers, we can map planetary positions using pure continuum mechanics. In this framework, the planets aren't being pulled, they are settling into the medium. This chart highlights the single equation that accurately predicts where these clusters form, the dynamic pressure drop. Position is a direct function of local density and scalar cavitation speed, the specific variables neutralizing ambient pressure. Planets settle as static equilibrium bubbles, locking into discrete acoustic shell boundaries where internal kinetic energy perfectly matches the system's external pressure. This explains why the telemetry clusters into sharp lanes rather than smooth ellipses. Those orbital tracks were always mathematical placeholders for a much more violent mechanical reality, the exact physical coordinate where a planet neutralizes the local pressure of the cosmic medium. The Sun functions as the primary impeller of our system, an active, violent thermal engine, forcefully pushing outward against the void. It sits at the center of the local bubble, translating forward through the galactic substrate while spinning with immense speed. This rapid rotation actively twists and shears the surrounding hypertense pressure field, radiating a massive, continuous outward thrust. This high-frequency kinetic engine carves out a massive core displacement envelope, generating the primary mechanical force that structures every planetary node around it. Looking at the inner planets, Earth serves as a perfect example of this pressure balance. We are not traveling in a closed gravitational loop. Earth is a stable node trapped in a specific pressure neutralization lane. It sits exactly at the radius where the Sun's outward thrust perfectly balances against the surrounding cosmic pressure. This top-down view illustrates how the Sun's active rotation creates a massive shear envelope. It sweeps the pressure field circumferentially, dragging the planetary node along an open, helical slipstream. Caught in the mechanical slipstream of the Sun's rotating pressure boundary, Earth is swept along its path by the shear torque of the medium. Our orbit is a byproduct of this motion. If the Sun's rotation were to halt, the rotational shear matrix would collapse, and Earth would immediately lock into a stationary, rigid radial standoff. Crossing the phase boundary to Jupiter, the physical state of the planet shifts. These outer gas giants operate as massive structural balancing nodes. This singular value decomposition tracks the kinetic energy density across the outer solar system. The data shows a strict quadratic decay, a sharp drop from a value of 463.58 at Jupiter down to just 96.07 at Neptune. This precipitous drop in kinetic agitation reveals that the gas giants are not free-floating bodies, they are mechanical anchors. Placed at mathematically predictable intervals, these stable masses absorb and redistribute the massive incoming pressure of the galactic medium. They act as the structural ribs of the solar bubble. By absorbing external shear, they prevent the inner solar system from collapsing under the weight of the surrounding cosmic environment. Beyond Neptune, the spatial pressure gradient settles into an ultra-low agitation near static baseline. This serene boundary exists because an immense force is pushing back against the sun's outward thrust, holding those massive planetary ribs tightly in place. This is the universal squeeze, the relentless inward crush of the ultimate cosmic substrate pressing against our localized cavitation bubble from all sides. The solar system operates as a highly pressurized closed equilibrium bubble, reacting moment by moment to the crushing weight of this vastly larger cosmic environment. This environment is dynamic. The macro-universe operates as a highly pressurized, directionally traveling field. Because the entire cosmic enclosure is in motion, our precessing solar bubble is physically oriented by the directional flow and pressure gradient of the universe moving past it. This mechanical geometry scales all the way to the galactic heart. Dense star clusters and the core of Sagittarius A star mirror these same impeller mechanics, driven by the same scalar pressure relations. Whether we look at Earth or a galactic core, the observed orbital frequencies are merely the mechanical exhaust of a pressurized system finding balance. From high-density DNA to the scale of gas giants, matter does not follow geometric lines in a void. It simply locks its geometry into stable standing wave nodes to survive the relentless, unyielding crush of the universal squeeze.